Hey everyone, and welcome back to the next session of the machine learning track for Edge Impulse's Imagine Innovators conference. Thank you for attending. We're super pumped you're here. We've got lots of great info to share. Before we get to this session, a few housekeeping notes. If you have any questions during the presentation, feel free to put those into the chat. We'll have team members monitoring the chat and responding to your questions as we go. There will also be time available for Q&A at the end of the presentation. So if you feel like you want to hold off your questions until then, feel free to do so. And lastly, if you haven't signed up for an Edge Impulse account, now is a great time to do that. It only takes a couple minutes, and you can do that by heading over to studio.edgeimpulse.com/signup, and we'll put that in the chat so it's easier to access. Once you create an account, you'll be able to put into action what you learned today as you build your own Edge AI models. Okay, so now that that's out of the way, on to the info about the session. In this talk, we have Moe Sani, who will be going through the visual anomaly detection for industrial use cases. Moe is a staff solutions engineer at Edge Impulse, where he works directly with customers and partners, empowering them to bring cutting-edge machine learning to a diverse range of industries. He has over 10 years of experience in the field of robotics, machine learning, and embedded systems, with previous roles including his time at Dyson, where he led the research and implementation of the first ML-based navigation system for one of their robotics products. His expertise spans AI, IoT, areas of predictive maintenance, smart automation, and many others. In all of it, he's focused on turning complex technologies into practical, real-world applications. This is going to be a great session, and I'm stoked to see what Moe has to say for us today. All right, Moe, over to you.
Thank you very much. Hello, everyone. In this session, we're going to talk about anomaly detection for industrial use cases. So what is visual anomaly detection? Basically, in industrial scenarios, sometimes you would want to see if one of your products is defected and has a fault on it or not. Like, you want to look at the images and see if there is any defects, if there is any damage in the product. Basically, imagine a human looking at the end of the production line and checking the products and testing their qualities. Now, we want to do this automated, and we want to check this by a camera mounted on the production line. The algorithm for this is visual anomaly detection. So the benefit of this algorithm is that you only need to train it with the nominal data. So here we have some ceramics, as you can see. So you only need to train the model on the good data and then deploy it to the target. And once it is deployed, it is able to basically detect anomalies, any cracks, any damages on your products. So now, what is anomaly detection and what are the use cases? We basically, in a nutshell, we want to detect and identify data points that deviate from the normal data that we trained on. So use cases could be detecting scratches, dents, or missing parts in your products. These are only for visual. So we are focusing on visual anomaly detection. We have anomaly detection for time series. You could go and check it out. This is outside the scope of current webinar. In food production, you could look at the spoilage, packaging errors, or missing labels or anything like that. In electronics, you could see if any components are missing in your production line. And pharmaceutical use cases, similarly, missing label, contamination, mold growing on your products. You know, you could just decide the use case and see wherever you need to basically detect if something is deviating from the nominal data, and you will get an alarm for it. So here in the picture, you can see the coffee capsules that I'm going to show you the project about this one. So the normal coffee capsule on the top and the damaged one in the bottom. The aim and the goal is to detect the damaged one without letting the algorithm see the damaged one, because in industrial use cases, it's normally very hard to train and find a lot of data from the damaged products. Imagine especially if you're producing something really expensive, or the damage is not very predictable. It's sometimes a dent on one side, sometimes missing screws or missing bolts and nuts and other parts of the product. So you can't really predict that. And that's why this algorithm comes in play. So the key requirements for this is you want to have high accuracy, you want to have low false positive rates of false detection, and you want to have a really a small inference time. And also because you want this algorithm to operate on the edge. This is whatever we do at Edge Impulse, we try to make it work on the edge. And explainability is another thing where you want to know why something is, not a good data, not a nominal data, and it is anomaly. There are plenty of algorithms that do this, visual anomaly detection, K-means, isolation forest, GMM algorithm, autoencoders. There are plenty of algorithms. I'm not going to go too much into this. Our colleagues have looked through this and decided to focus on the patch core algorithm here in our platform. We have a couple of different versions, but in this presentation, I'm going to focus on the patch core algorithm. So in the platform now, we recently released the HD version of the anomaly detection. This is very high resolution. It will mean that each pixel size could be small, so that the algorithm can focus on a very tiny area and will pick up tiny minor defects and details in your images. So each cell size can be small while keeping the frame rate high and inference time lowish as usual in our platform. So on the right, you can see the algorithm doing the anomaly detection on this valve. So the good thing about this is that you can basically see where the algorithm is thinking the anomaly is happening. So on this valve, there is a missing part on the bottom section, and you can see a heat map or a cell is showing that area by red colors. That's showing the anomaly. And this is a comparison table between the new FOMO-AD, the high resolution version, or HD version of this compared to the previous one. And you can see it has better performance and more accuracy in there. So make sure to check it out in the platform. I'm going to just quickly go through how it works. We basically, a patch core, we basically divide the image into small patches, and then we extract information from these patches and store it in the memory banks. And then later on, when you pass in a new image of the data that it hasn't seen before, it will go and compare it with the existing sampled, the samples of the patches that are stored in the memory bank, and do a k-means nearest distance, and will basically compare and extract all the anomaly scores out. And that's how we decide if the image has an anomaly or not. One of the good use cases that you could do in the platform is mixing anomaly detection with object detection. This is really powerful combination because in a lot of industrial use cases, you you don't want to do anomaly detection in the whole of image. You want to do it in certain areas, and you could decide and find that specific area by running an object detection model. So here you can see a car wheel and all the holes. We have trained the model to define all to find basically all the holes in this car wheel, and some of them that have missing nuts will basically be identified by this heat map there, and anomaly detection would be a good use case. So think about your own use case here. If you have a manufacturing line that you're manufacturing something, and you have a likelihood that, or you have a guess that your anomalies or your sensitive areas might be in specific parts of this product, you could then train like an object detection model and then apply the anomaly detection on it. This is basically another use case of it, because if you combine object detection and anomaly detection, then you could use this algorithm on moving parts as well. If your products are moving on a conveyor belt, you could then first do an object detection. We also have an object tracking feature coming up, which is really important and useful. So you could combine all of these together and then do an anomaly detection, which makes your life much easier and will increase your throughput. You don't have to stop the manufacturing line for this. This is a demo we built recently. This is the basically a turntable showing the coffee pots are turning around. And on this screen, you can see the object detection is happening first, and then anomaly detection is happening on the right-hand side of the screen. And this is all running on the device on this Qualcomm Dragonwing industrial AI camera. So I'll quickly pause here and go back to Studio and show you how we can actually build such a project. So I have two projects if you wanted to focus on combining an object detection and anomaly detection. So I have two projects here. One project is doing an object detection. So you're basically preparing a data set with lots of bounding boxes around it, picking whatever area of interest you want to do this anomaly detection on. So you prepare that. I'm not going to go through all the details because there are other talks and webinars that go into the details of different parts of the platform. I just want to focus on anomaly detection sections. So after the basically data acquisition tab, you go ahead and basically create and train your object detection model. So this is our object detection, and in the model testing, we're getting 86% accuracy, which is fine for this project. It's just a quick one to show and test this. And we are using YOLO Pro here, which is the new features in our platform. Now, the interesting part of the project is visual anomaly detection. For this section, you provide a lot of cropped bounding boxes of the images. You provide a lot of cropped images, and you only need to provide the nominal data. So now in my training set, as you can see, there's lots of images of the capsules, and it could be more. I just wanted to quickly test this. You could provide a lot of different varieties, different colors, different backgrounds, different lighting, and all this if you wanted to make your model more robust. So, but the good thing is you don't have to go ahead and find defects in your products. So in my testing data set, I have some defects just to test, and make sure this algorithm works. Some of them are like this. They have a damage in the middle. Some of them have a bigger damage here, and some of them are fine. So we can go ahead and train a model, visual anomaly detection model. That's one of the blocks that you can select from here. And for this example, I went ahead with grayscale, but you could do your tests and experiments and see which one works better. And I'm using patch core algorithm in this section. As you can see, the inference time is only 26 milliseconds and peak RAM usage less than 5 megabytes. And at the end, the model testing shows me 100% accuracy. Of course, this is a limited data set, but just wanted to show you the concept here. So this is, let's look at this. This is one of the nominal, no anomaly data that obviously the model hasn't seen it before. But this is one of the damaged capsule that you can see the overlaying heat map kind of shows where the damage is, similar to this one and other ones. It's really interesting features. I already know a lot of customers are excited to talk and start using this. So yeah, make sure to try it. Now back to our slide deck. Make sure also go ahead and look at our data sets. We have a lot of, my colleagues built a lot of high quality data sets for anomaly detection as well. You could start, if you don't have your own data, you could start playing around with these data sets here. And I wanted to give you some points about best practices here. So there are some misunderstandings around that. People think that the FOMO-AD or the visual anomaly detection algorithm works magically on everything. I wanted to highlight that there are some stuff that you need to pay attention to. First thing is consistency. Make sure the background is similar. You can't train a model on a plain background and then expect the model to, in the testing phase, expect the model to ignore the background if the color changes or whatever. If you wanted to make it robust against the background changes, you need to have different backgrounds in the training set as well. Try to cover a lot of variations in your data set. Try to have images from different angles of lighting, different colors, different background, different sorts of products if you have it, different angles of the product. So try to add as much as variety as you can. This will improve the outcome. Avoid data leakage. Make sure not to have anomalies in the training, because then you're training a wrong model. Image size is very important. You need to make sure the image size in your training and your eventual deployment are matching. You have to kind of do a same cropping of the image. You can't have different aspect ratios or different zoom in your lenses and then expect the model to work. So these things are important. It's kind of a pre-processing step. And data augmentation is another thing. If you didn't have the ability to capture a lot of different data, you could augment the data. There are other webinars that show you how to do this. You could refer to them. Another thing is automation pipelines. So you could basically have a pipeline that once you identify an anomaly data, you could have pipelines that alert the team members then an engineer investigates the model, and if it is actually an anomaly, and adds it to the data set, and then you kind of have some sort of automation going on, and you could train a new model, or if the existing model is not performing well, you collect a little bit more data. So these things, it's good to keep it in mind, because normally once you train a model first and deploy it in the production line, often it's the case that you haven't completely captured all the cases. So there are going to be new cases coming up that you haven't thought about it. So you will have to kind of have this pipeline of collecting more data up to some point. And as we talked earlier, there are some common pitfalls that we said. Data is not being representative. Some customers, some users, some developers sometimes do this mistake of like having mixed quality backgrounds, mixed resolutions, mixed angles in their images from testing to the training, and this would mess things up. So pay attention to these, and try to capture a lot of samples. The more you do, the better it is. And some people kind of ignore the inference size speed. That the good thing about the platform is that it would always show you what's your inference time. So keep an eye on that if you're eventually aiming to deploy this on the device. And next steps, if you're interested in this topic, make sure to have a look at our docs page, go look at our data sets that we have, and start building your own project. That's it from my side. Thank you very much. And if you have any questions, let me know and we can answer. Otherwise, let's connect and keep in touch. I'm happy to answer any questions here.